How's everyone doing?
Good. How are you doing?
Hanging in there. All right. Let's see. So I think you're done turning everything in until the final exam. So hopefully everybody's turned in their labs. Most people turned in their homeworks. I want to talk a little bit about the homework today. Actually, didn't get that many people over the past few weeks coming in to ask details about the homework. I think a lot of people kind of started it on the weekend and then got stuck because it was. Verilog is pretty fun stuff, and that fun can go in quotes or not in quotes. Um, this is a fundamentally different thing from everything else in the course. Um, Pretty much everything we've done in 250, and for the most part everything that we do in 120 is very sort of procedural. Here's a problem, here are the steps you follow to get to a solution. Even these large problems that take a half hour to do, like state machine synthesis, we were able to outline a series of steps. First, decide how many states you have, decide how many flip-flops, what kind of flip-flops, make a state assignment table. And if you follow these steps, if you keep turning the crank, right, eventually an answer pops out the other end. And this unit where we're writing Verilog to describe circuits, this is a fundamentally different feeling. This is not something we can describe a step-by-step procedure in order to get you to an answer. It's purely something that you have to keep working and let your brain do its magic. Let it come up with the wirings, the intuition, the insights, so that you can get to a solution. And the first few programs that you try to write in Verilog or in C, if you're taking a programming course, or in some other language, um, probably no idea how to do the problem, right? So you work on it and you try some things and you simulate what you've done. If you're in Verilog, you put it in the Aldec tool, you run it, you look at the timing diagrams, you scratch your head and say, that didn't do what I expected. If you're writing in a programming course, you write your code, you compile it. If it doesn't compile, you fix those issues, you run it. That didn't work, what's going on, right? And it's a really lengthy process, particularly in the beginning, but the more you do it, the better you get at it, because your brain starts to figure out intuitive ways of thinking about problems, and you see a problem and you start to think, oh, I could use a shift register here, oh, I should build a state machine, oh, I can do this with combinational logic, right? And you're going to encounter this in engineering 270. Every problem that we do is going to be like this. Very, very little of 270 is mechanical. There's a few things where we convert things to binary and so on, but all of the programming we do in 270 is going to be assembly language programming, is going to be the same kind of creating out of nothing. And the only way you get to where you can do that is by trying and failing and trying and failing, and then succeeding a little more every now and then, and building up to that. You're going to get this if you're computer science. This is what all of the 200 level CS courses are about. Whatever your major, you're going to do 3/4 of calculus-based physics. This is what physics feels like for most people. It's no longer a case where, here's the steps I have to follow, I'll do each of those, there's my answer. You're going to get problems and they're going to look like nothing you've ever seen, and it's the most frustrating thing in the world. This is why I hated physics when I was a student. Because I'd go through the book and I'd go through the lecture and I'd go to the TA section and I'd see the problems worked out and I was convinced I understood it perfectly. And then I'd sit down the night before the assignment was due and I started working on the homework, and it's like, what the heck is this? This has nothing to do with anything we've talked about in class. This has nothing to do with the problems we've solved, and I would get really frustrated. And this is a typical experience. Um, And when you leave Clark and you transfer to university, chances are all of your courses are going to be like that, right? Certainly all the ones in your discipline, engineering, computer science, and so on. So it's a different modality of learning and solving problems, and it's the modality that makes you so valuable to future employers, right? Because if an employer has something to do and it can be described by a series of steps, and that same series of steps always gets you to a solution, they're not going to pay you $100,000 to do that. They're going to hire someone to write a computer program to do it, right? Your value added to a future employer is your ability to solve problems that you haven't already solved before. And that's what you're trying to get out of college, I think, more than learning Verilog, learning K-maps, learning how to program in Python, learning history of world civilizations, right? Those are tools to help you basically learn how to learn, right? You're trying to get that second level of problem solving skill, and that's what's going to serve you well down the road. So the punchline of all of that is, like, if this feels like a really kind of wonky unit, the Verilog stuff, that's okay. It is pretty wonky. If it felt like this was a higher bar than some of the other stuff, and you had less idea how to do this, that's kind of a typical experience, and it's reflective of the fact that this is a fundamentally different type of subject that we're working with. Um, but what I've seen on the homeworks is mostly people making a good effort, and that's the real key, right? And in particular, the problems where there was not a solved version, so like the traffic light problem and the ALU problem, you didn't have a solved version to modulate. The other questions, question one, there's a solved version, and then the unsolved one is a slight variation on that. So you can mimic what was done in the solved problem, get a solution to the unsolved, without really knowing why the solved one works, and therefore why the unsolved one works. But those last two questions in particular, 7 and 8, those you don't really have the solved version to start from, so you're kind of starting more from scratch. And 7 we talked about in some detail, and we talked a little bit about 8. And so let's just take a look
Which
at.
one did you grade?
So I graded 7 and 8, and if you got one of those pretty close to correct, and made a good effort on the other, you got 20 out of 20. If you were on the right track on if you got one of those correct and you had a good start on the other one, you got like 18 out of 20. If you didn't do either of those, or just kind of had an outline for those, then I looked at the other ones, and if it looked like you were doing the right thing on those, then I gave a bunch of points for that. But mainly I was looking at 7 and 8.
I had something to say about 8.
Yeah.
So when you graded mine, you were like, I don't think this will work because I use ternary operators to assign the output depending on what operation you wanted to do.
Mm-hmm.
It actually does work. I think you said you thought it wouldn't work, but I tested it and it does.
Yeah, and I didn't take off points for that. But you should be getting a compiler from that, because I think what you were doing was you had 3 statements. And each of these, was a ternary operator. But the compiler should complain unless these things are perfectly in harmony, because you're simultaneously asking it to give out different values based on different expressions. And I tried copying your code into an instance of Aldec, and I didn't get all the way to a solution because it was all coming out on one line from the PDF, so I need to chop it up and play with that some more. But I'll play around with that. And like I said, I didn't take off points for it. But normally,
They're like that, but not on that problem, and I don't know why.
say that again.
So on other problems, I double ternary.
Mm-hmm.
Yeah. Like on a few other problems, I got an error for trying to assign something multiple times, like you just stated.
Right.
But I'm not sure why I didn't get it here.
So it may be that the assignment statements were all in harmony, and the compiler is smart enough to realize that you're not actually trying to give it three different values, but that you'll give it the same value in each case. Um,
Could having the lesser than sign have something to do with that?
so you definitely want the less than equal because this was inside an always block, so it was happening in response to an event. Um,
No, but I'm saying, could it having the lesser than allow the compiler to because it's doing all three of them at once?
well, that's the reason it normally gets unhappy about this. Is because all three are supposed to happen simultaneously. It's not like first do this and then this and then this. Um, but yeah, I'll go back and look at that and let you know because I was curious about that. So yeah, that was interesting. So one general comment on the homework, right? So you have a software tool you can use to take the Verilog code you write and simulate it. And so there should be no surprises, right? You should know absolutely whether your code is correct or not because you can write the code, compile it, simulate it, look at the timing diagrams that come out and confirm whether it's doing what you wanted it to do or not. Um, but that's assuming you understand what the question is asking, and sometimes that's part of the challenge. So write Verilog code to implement this function. So this can be done with an assignment statement, and it's very similar to this. It's a different logical equation, right? So not A ANDed with B, ANDed with not C, etc., etc. But it's that straightforward. Um, Positive edge trigger T latch and the SR flip flop. I didn't see a whole lot of problems with that. Same thing with the counter. So a lot of the confusion started in with questions 5 and 6. Verilog code to implement a 3 to 8 line decoder. So what is a decoder?
It's a mux.
Yeah.
Emux.
So you have 3 select lines, and you're choosing one of 8 output lines to carry the value of an input.
That one confused the heck out of me.
Yeah. So you gotta know what it's supposed to do first of all. Sorry. Go ahead. Say again.
Oh, my bad. I said those two took me longer than all the other ones combined.
Yeah, yeah. Well, 7 also takes a long time.
What they were supposed to do.
Yeah.
Seven took just from all the ifs.
Right. Let's see. So right, you can write a truth table for this, but you can also think about it kind of functionally, like behaviorally, which is, depending on the value of select, we want we want one of these outputs to be equal to in, and the other outputs to be some default value, right? Now this says active high, so we can interpret that several ways. We can interpret that to mean that, if we call these outputs Z0 through Z7, then if select is equal to 111, we interpret that as being a 7, and so we want Z7 to be equal to in, and Z6, Z5, all the way down to Z0 should be 0. So active high has a lot of different meanings. I think I only had one person ask me about this though, but it's most likely meaning that if we interpret these ones as being logic 1 and 0 as logic 0 when we form our binary number, then this is the number 7, and so we want output 7 to copy the input, and the other should be 0, which is the inactive state, right? High is active, 0 is inactive. If this was an active low, then probably the outputs that aren't selected would be in the high state, because that's the inactive state. And sometimes this select line would be reversed. 0, 0, 0 would mean we're selecting output 7. 1, 1, 1 would mean we're selecting output 0. Those are tweaks on the Verilog code, though, right? That just changes whether you put a 0 or a 1 here and how you index your output and so on. It doesn't change the fundamental structure of the Verilog itself, so I wasn't too worried about how you interpreted active high or active low in the next one. But we can do this with, output by output. So Z0 equals, if select is equal to 0, it should be equal to in, otherwise it should be equal to 0. So we can do this as an assignment statement. And we can set Z1 equal to, well, if select is equal to 1, then Z1 should be equal to the input, otherwise it should be 0. And so we can write 8 of these assignment statements, and that should give us a good 3 to 8. And depending on the value of select, right, one of these outputs will be set equal to in, and the others will be set equal to 0. A number of people implemented this as a clocked circuit. They had a clock that was called enable, I think, in most cases, and then had some registers set up, and then some if statements to set the value of the register based on the select value. And you can do that too. You can get varying levels of fanciness. You can make an array of output bits and index them with the select value if you set it up right, and so on. But this is sort of the brute force approach to doing that. So that's a decoder. The encoder is even trickier. So an 8 to 3 encoder. So here we've got 8 inputs. And we can call them input 0, input 1, down to input 7, and then 3 outputs. Well, how do you pick a 3-bit output value based on 8 inputs? Well, you can look in the text. Is it wrong if I wrote out the values according to the truth table? Nope, that's totally fine. On this one, I mean, you can take the truth table for this circuit and write combinational expressions that give you each bit. And that's just sort of this difference between structural and behavioral definitions. And you can almost always go back to, the pre-Verilog approach to things and write equations or sum of products, product of sums, and use that to describe your circuit. So yeah, that'll get you a good solution too. When you understand behavioral aspects of it, then it's just a little easier sometimes to do that. So what does an encoder do? Well, there's different kinds of encoders, but we talked about one called a priority encoder. And if you go to the textbook, and search for encoder, here's a sample 74148, and this is a priority encoder. Okay, it's a very, very interesting sort of behavior. Forget about active low, active high, all of that stuff. Just look at the general behavior from this truth table. You have 8 inputs, you have 3 outputs. Okay, in this case right here, most of the inputs were high, but this input was low. and that determined that the output should be high, high, high. In this next to the bottom row, most of the inputs were high, but input 1 was low, and input 0 had no effect. And the output was high, high, low, binary 6. In this third row from the bottom, most of the inputs were high, except for input 2 was low, and then we didn't care about inputs 1 or 0, and the output was high, low, high, binary 5. So what this circuit is doing, this is a priority encoder, right? It starts from bit 7, and moving to the left, it asks, what's the first bit I encounter that is low? And in this case, bit 7 is the first bit it encounters that's low. And so this is going to output a 7. Okay? This device is active low, so when we want to output a 7, we want 3 bits asserted. Active low means to assert a bit, make it low. So the output is low, low, low. That corresponds to the binary number 7. This is telling us bit 7 is the first bit we find that's active, which in this case means low. In this row right here, starting from bit 7, the first bit we find that's active, meaning low, is bit 6. And so this encoder should output the value 6. Well, how does it do that? 0, 0, 1. Active, active, inactive. Okay, this is sometimes called negative logic. So if we come down here to this row, starting from bit 7, let's find the first bit which is active. This is inactive, inactive, inactive. This bit right here, bit 4, is the first one that's active, low. So the output from our encoder in this row should be 4. Well, how do we write a binary number 4? We want this bit to be active and these two to be inactive. So low, high, high. All right, so that's the active low part. That's kind of a weird thing on there. So if we ignore this business of active low, let's just think about this for plain old positive logic active high. And let's think about I'm still going to write these from left to right. So let's just write down different input values and let's see what the first high bit is. So here's one possibility. Here's a second possibility. Here's a third. And so on. All right, those are all our possible sets of inputs. In this case, starting from bit 6, what's the first bit that's equal to a 1? Sorry? Starting from bit 7, what's the first bit that's equal to a 1? It's a 7. In this case, the first bit that we find that's asserted is a 6. In this case, it's a 5. In this case, it's a 4, and so on. In this case, it's a 0. And in this case, we got to decide what to do. So maybe we'll just make this a 0. But you gotta make a decision. This is all part of that discussion thing that you do in addition to listing the bare Verilog code, right? Talking about what the code does, what the circuit does. So then the output is just the binary encoding of this information. What's the first bit starting from bit 7 that's asserted? All right, so how do we make a Verilog circuit that produces this output in response to this inputs? And you can get into wildcards in your pattern matching. You can use X's and all kinds of things that we haven't talked about. But we can do this just with good old ternary operators, right? We can still just use an assignment statement. And it's a little stranger looking, but we can do it. And again, this is looking at...
bits up and assign it out.
Sorry, say again?
Can't you just add up every individual bit and assign it to that?
I'm not sure if adding will get you there. For example, in this case, we want our output to be 5, regardless of what these values are here. So they could be all zeros or all ones or a combination. The reason we want a 5 is because this and this and this have the pattern 0, 0, 1. It's the fact that these two bits are 0 and this is 1 that makes the output a 5.
Okay.
But if you mess around with this a little and look at how the output bits relate to the inputs, we can start to see some patterns. For example, this least significant bit, and I'm not going to worry about this last row for now, but this least significant bit alternates, right? It's a 1 if input 7 is a 1. It's a 1 if input 7 and 6 are 0 and input 5 is a 1. It's a 1 if these first 4 inputs are 0 and the fifth input is a 1, and so on and so forth. And so we can do something like this. So let's suppose this is Z0, Z1, and Z2. So Z0 can be assigned the following. If I7 is equal to 1, then Z0 should be equal to 1. Otherwise, it should be set equal to a different expression. This different expression is going to be if I6 is equal to 1. And we know that if we're evaluating this expression, I7 was not equal to 1. But if I6 is equal to 1, we should set Z0 equal to 0. Otherwise, we should set it equal to I5 equals 1. Set it equal to a 1, otherwise some other expression. So you nest these things up. If you ever did if statements in Excel, this is what your if statements end up looking like. Because Excel basically uses a ternary operator for its if statements. But we can write this differently. So if I7 is a 1, we're going to set it equal to 1. Otherwise, we'll set it to, if I6 is equal to 1, a 0. Otherwise, we'll set it equal to, if I5 is equal to a 1, otherwise, and so on and so forth. And you can follow that down to I0 equals 1, in which case we should set it equal to a 0. Otherwise, none of these were equal to 1. We're in this last row, and if we're going to make the no bits are asserted output equal to 0, we'll just set it equal to 0. So that's a big, long, monolithic assignment statement that's a neater version of this, but is basically doing the same thing. And the way this is structured, if bit 7 is a 1, we'll get a 1. Otherwise, bit 7 is a 0. If bit 6 is a 1, we'll be in this row, we'll get a 0. Otherwise, if we're down here, bits 7 and 6 are both 0. But if bit 5 is a 1, then we're in this row, so we're going to set the output equal to 1. And you make a similar looking statement for Z1, another one for Z2, and those three assignment statements will get you your 8 to 3 encoder. And like I say, this is positive logic, this is active high. If you want it to be active low, then you change these to zeros, and you probably toggle the output values. And if you're trying to do this, right, start with a smaller problem. Make a 4 to 2 encoder, or make a 2 to 1 encoder, and make it active high, positive logic, so you don't have to worry about flipping things, negating things, and so on. Right? Start with a simpler problem that you might understand better to figure out the Verilog aspect, right? The newest part of the whole problem, and then start building from there into a more general module that will get you to what you're actually trying to implement. So yeah, that's kind of a crazy problem, but that's one way to do it. The intersection we talked about last time, and again, the probably most straightforward way to think about it is in terms of states, and just thinking of green and yellow lights, and the fact that at any moment there's either a green light on somewhere or there's a yellow light on somewhere, assuming they're never all red, and that leaves you with 6 states. And for each of those states, you have 8 possible input combinations, because you have 3 car sensors. So 8 states, or 6 states, 8 inputs, that's 48 arrows on your state diagram. Don't draw a state diagram, right? It's a mess. But if you start making out a table, and I saw a lot of people doing this, if you start making out a table of, you know, if I'm in the eastern green state, and there's a car to the east, then I should stay east green. If I'm in east green and there's no car to the east, but there's a car to the south and no car to the west, then I should go to east yellow. And as you start writing these out, right, and forget about Verilog, just you know, piece of paper, write out these different states and input combinations, you start to notice that a lot of times you're doing the same thing for different combinations of inputs in state. For example, if I'm in east green and there's no car to the east, I'm going to east yellow. Doesn't matter if there's a car to the south, car to the west, car to the south and the west, or no car to the south and no car to the west. If I'm east green and there's no car to the east, I can just say I'm going yellow. And so you start being able to prune a lot of your you know, decision tree of sorts. And you find you don't have 48 cases you have to deal with. It's a lot smaller number.
18.
Sorry?
18.
That sounds familiar, actually, yeah.
3 lights and then 6.
Yeah.
6 different.
Yeah, so for each state, there's well, for each of your green states, right, there's either you're going to stay green or you're going to go yellow, right? And so it's really, you know, one if statement. If this is true, then I'm going to go yellow. Otherwise, I'm going to stay green. And for any yellow state, right, you know that your next state is going to be, you know, someone is going to turn green. So yeah, that pares it down quite a bit. And you know, getting good practice with an editor of your choice, lots of copy and paste here. Most of your statements are going to look like other statements, and the biggest trick is really sort of, you know, not making any typos. Because if you make a typo, it's all over. It's pretty hard to debug at this stage. But you know, again, this is where you know, you want to be explaining what you're doing, not just typing in some Verilog code and saying here you go, but explain how you're getting there, right? So that I can see your work and your thought process and say, yeah, this is good, this is on track, that kind of thing. And then the ALU we talked about last time also, and that can also be you know, 3 assignment statements done as a single ternary operator. So if you have a select function, right, you can you know, assign out equals function equals 1, If function's equal to 1, let's assign the output equal to a plus b. Otherwise, if the function's equal to 2, let's assign it to a minus b. Otherwise, let's assign it to a times b, or whatever you choose. So it's not a major part of the course, right? You'll probably have a Verilog question on the final, but as I said last time, this is probably the only time you'll encounter Verilog at Clark, and if you're double E, you'll encounter it at other courses. If you're computer science, you may encounter it in some elective classes. You may encounter it on the job. But
or a hobby,
or a service learning project, where you're trying to write some code to do something or build a circuit to do something, and you can do it with Verilog a lot easier than building it on a proto board. So let's talk a little bit about this. A lot of technology is about code reuse. When you're programming, you don't want to constantly reinvent the wheel. So if you need to sort a set of numbers, right, you find a library of sort routines and you pick something from there. If you're doing assembly language programming and you need to do a Fourier transform, you usually don't write it yourself. You find a library and you use it from there. School is kind of different, right? Because school we're asked to reinvent the wheel constantly. That's for learning and practice and assessment. But in practice, right, we like to use our minds for more creative endeavors. And the stuff that's already been done, we just sort of like leverage. And so there's a good website to look at called opencores. And opencores is basically an open source site for Verilog and VHDL code. And so we can click here on projects. And I don't know, let's say you want to do arithmetic. So, and let's specify a language. Let's go with Verilog.
Can you program FPGAs in other languages that weren't designed to be HDLs, like C++?
Well, yes and no. So there's something called System C, which is in some way a way to go from a C program to hardware. It's an open question at this point. It's kind of a bit of the holy grail, or a holy grail, to be able to take a program written in a standard programming language like Java or Python or something and convert that into hardware. And there's some success. Say again?
It's kind of a holy grail to do with anything.
Well, yeah, totally. Yeah. But with procedural programming languages, it's tricky right now. It's a cool research area. It's an area I like spending some of my brain power on. But the reason we have Verilog and VHDL is because if you know that you're describing a piece of hardware, you can make the task easier. But yeah, to some degree, things like System C will work towards that, but varying degrees of success. So I don't know, what is this, an 8-bit Vedic multiplier, so Deep Space Nine or something. So let's just browse this. So here's a full adder. Well, that's not terribly exciting, right? Um, so full adder inputs A, B, and carry in, outputs sum and carry out. Well, it uses a couple of half adders and cobbles together a carry out from the carries of the two half adders, and you know, there's a Verilog module for a full adder. So that wasn't tremendously exciting. Here's a 12-bit ripple carry adder, so it's using a pair of 6-bit ripple carry adders to make a 12-bit. And, you know, the 6-bit ripple carry adder is using a bunch of full adders. But, you know, say again?
These guys
Yeah.
are using them all.
But let's look at something more profound. So let's look at processors. So 16-bit microcontroller.
You can fit like whole computers onto these things.
Oh yeah, definitely.
There's a thing called Mister, which is kind of one of these open source projects.
Yeah.
A FPGA, and you can use it to emulate old game systems with it.
Cool.
And impressive enough, there's actually a 486 and a Pentium core.
Very cool. Yeah, the amount of hardware available in a modern FPGA is staggering. And things like, you know, 32-bit processors and so on that seem astounding will pretty easily fit in a lot of these devices. And, you know, you can type on your keyboard and spec out a processor and clunk it into some hardware and run with that. I mean, that's just... it's a whole lot nicer than putting things on proto boards. I am like really horrible at navigating this tree. But I did this last week and found some cool processors. Let's go with the Z80. Z80 is awesome. So, you know, lots of good documentation on here and examples of how to use it. And a lot of this stuff comes with, you know, so this Z80 comes with like its own development framework and so on and so forth. I really just want to see some good old Verilog code in here. There we go. All right, so let's take a look at the ALU, right? So this is designed for an Altera system, but you know, it's Verilog, it's generic. So here's the ALU, and it's got, you know, all of these inputs and outputs. And what is an ALU, right? Well, it's question 8 on our last homework, right? And you put in a couple of inputs and you put in a function select and it does something in response. Well, this is a more powerful ALU, right? This can do left and right shifts and logical operations and load preset values and generate parity bits and all kinds of stuff like that. And lots of setup, right? Specifying what the inputs and outputs are. This looks like a 4-bit ALU, which is pretty standard. And then, you know, a bunch of assignment statements. And it's clocked. And depending on the operation that you're trying to do, it will do different combinations of your inputs to generate outputs. So, you know, this is a hefty chunk of code. And if you get through the documentation and figure out how this works, and, you know, it's got the system diagram kind of view of how you hook it up to the outside world, you don't have to write this yourself, right? You can download this and use it. There's a shifter, so for a 32-bit module. So this is typical of the kind of stuff that's available, and you know arithmetic cores, communication systems, coprocessors, lots of crypto stuff, right? Um, Hardware is a really nice way to do cryptography, and if you're trying to build a system with an encrypted hard drive, every time you send or receive information to or from the hard drive, you got to go through an encryption decryption. That's expensive to do in software. That makes your operating system really slow. It's really nice to have hardware to do that. And if you have something like AES or Blowfish or something like that, that's fairly secure and involved, right? It's putting this inside hardware is a really nice way to go. Signal processing, ECC, which is, I believe, error checking and correcting. Lots of memories. Memories don't always work really well in FPGAs because memories are so special purpose. But video controllers, so you want an HDMI controller or a VGA driver or something like that. So all this stuff is out there, and it's open source, and this has been around for a long time, kind of before open source started to be such a popular thing. But people in this area realize that, like, we're spending a lot of time making this stuff. It'd be really nice to be able to share this with other people and take advantage of what other people have done and use that in my project. So it's very fun doing these things yourself, right? Writing a VGA driver from scratch in Verilog is a fun exercise if you're trying to learn Verilog and learn how VGAs work and so on. But if you just want to use that because you're trying to make a video game, you can just pull down a core. And there's companies that sell IP cores, and that's their whole business. That's their product. They just sell you intellectual property in the form of Verilog code for implementing different functions. And that's totally viable. All right. Questions on any or all of this stuff? All right. Well, let's do a few-minute break, and then I want to come back and I want to talk about some other aspects of doing arithmetic. So we're going to leave hardware definition languages and go back to more of the Chapter 9 stuff, adding, subtracting, multiplying, things like that. So let's take a short break, and we'll come back and do that. let's talk more about arithmetic. So again, this is unrelated to Verilog at this point. Let me put a reminder out there. So final exam is Tuesday, 12 o'clock to 1:50. So that's a week from today. That's the standard.
Talk about the final Thursday.
Yeah, we'll talk about it Thursday. I'll post some kind of topic summary, but it'll be a cumulative final. It will be more heavily weighted on things we've done since the midterm. So state machines, sequential circuits with clocks, timing diagrams, things like that. But it will also, potentially include some of the earlier stuff, K-maps, product of sums of products, stuff like that. But I'll put together a topic list and post that on Canvas, and we can go through it on Thursday. And probably my plan is for Thursday to mainly be a wrap-up and questions and so on and so forth. Because I don't think there's much point in going through new material the last day of class. So it'll mostly be talking about the exam. And the exam will be similar in style to the midterm, so you'll download a set of questions and you write up your answers, upload them as a PDF, but with more time.
We could watch a movie on Tuesday.
We could, yeah. There's definitely some good Digital Logic movies out there. Yeah, we could find something. All right. So addition, right? We know how to add numbers. Right, we just go column by column. 1 and 0 is 1, 0 and 1 is 1, 1 and 0 is 1, 0 and 1 is 1, 0 and 0 is 0, 1 and 0 is 1. Bingo, we're done. How hard can it be, right? Well, that was a pretty easy way to do our addition, because we never had to do any of these carries going from one column over to the next, right? But if I had added something like this, now things get a little trickier. 1 and 1 is 0. I have to carry the 1. 1 and 0 and 1 is 0. I have to carry the 1. 1 and 1 is 0, and I have to carry the 1. 1 and 0 and 1 is 0, and I have to carry the 1. 1 and 0 is 1, and that's a 1. I feel like I didn't do that right. Yeah, I guess I did. And we know how to build circuitry to do this. We can use a series of 1-bit adders and put our incoming bits into the top of each, and have the carry out from one adder go to the carry in of the next adder, and then get our sums on the bottom. And so this kind of adder we've mentioned is called a ripple carry adder. And it's a ripple carry because in this case, for example, we got a carry out of these first bits. 1 plus 1 was 0 with a carry. That carry kind of rippled all the way down to here and caused this output, which would normally be a 0, to be a 1. And there's no problem with the hardware doing this. It can ripple that carry along, but there's a performance issue. The performance issue is, if I were to just have 6 people playing the role of an adder, and I just tell each person, add 1 and 0, add 0, 0, add 0, 1, right? They're all going to come up with the correct output bit in this case. But in this case, This person would say, okay, 1 and 0 is a 1, that's fine. This person would say 0 and 0 is 0. They would have the wrong value for a little while. Eventually, they're going to be told, oh, you have to add an extra 1. And then they'll say 1 plus 0 plus 0. Okay, that's a 1. And they'll get the correct bit. But that won't happen until they're told that there's a carry. And the person over here to the right who's adding a 0, 1, well, they're going to say the output's a 1 and there's no carry. And it's only when they find out that they've got a carry coming in that they say, oh, 1 plus 0 plus 1. Okay, my output should be a 0. Oh, and by the way, person next to me, you have a carry coming in. And so the time it takes for this bit to be correct is pretty significant. This bit is not correct until this adder realizes it's got a carry coming in. And that carry doesn't appear until this adder realizes it's got a carry coming in, and so on. And so if you have a 64-bit ripple carry adder, and let's say it takes 5 nanoseconds for a 1-bit adder to generate a carry, potentially that's going to be 320 nanoseconds before your 64-bit sum is correct. And this is an eternity, right? This is about a third of a microsecond. You're running at 3 megahertz, which, in today's terms is snail pace. And addition is pretty fundamental, right? We do a lot of adding of numbers, but where else do we use addition inside a computer besides adding numbers together?
For statements.
We use them in for loops when we have to increment a counter and control an iteration like that. Where else? Where do you use addition? Go back to like elementary school and you learned how to add numbers, probably in decimal rather than binary, but you learned how to add numbers. And then you moved on to another subject and you had to know how to add numbers to do this other subject.
Like algebra?
Even before that, think about multiplication.
Repetitive addition.
Yeah.
Multiplication.
So when you do something like this, right, well, we do 21, 11, and 8, and then we do 7 times 4 is 8, and 12 is 14, and 9, and then we do 7, 32, and then you got to add them all up. And that's tricky, right? So if you had 12-digit numbers, you would have 12 things down here that you have to add up. Well, this one's pretty easy. This is just going to be a 1. And 1 and 8, that's pretty easy. That's 9. But, 8 and 4 is 12, and 7 is 19. And I could get bigger carries than just a 1 out here. If I had, a 9 and a 9 and a 6, I would have, a 20-something. I'd have to carry a 2 over. And so a lot of what we spend our time in computers doing is addition, partially because we do so many multiplications. And when we have real numbers, we store these numbers inside a computer using scientific notation. So some mantissa times, something to an exponent. So regular scientific notation, 1.7 times 10 to the 5th, and we multiply that by, 2.4 times 10 to the 23rd. And so you have to multiply these together, and that multiplication involves an addition. And then we have to add these together and say this is times 10 to the 28th. So addition is like really, it pops up in all of these different operations. When you want to compute a sine or a cosine or a logarithm or some kind of scientific function, we use what's called a Taylor series. You get that into Math 150 something. But this is a collection of terms that get calculated and added together.
You mean like a summation?
Like a summation, exactly.
So that's what a Taylor series would be?
Yeah, Taylor series is a summation that gives you the value of a function. So for example, when you want to calculate e to the x, it's, I'm going to mess this up. I'll do an equals question mark. Something like that, right? And so you know, these factorials get big really quickly, so these terms start to get really small. But if you take, you know, maybe the first 10 of these terms and just add them up, you get a really good approximation for e to the x. And that's how computers generate values of these scientific functions like exponents and trig functions and so on, is by using expressions like this. So fast addition turns out to be a key to doing fast arithmetic in general. And one of the big impediments to doing fast addition is this whole issue of rippling a carry from one side of your circuit to the other. And so people have looked at ways to speed up addition. And it's really about the carry terms, right? You can add 2 bits really quickly. It's a little bit of logic. You've built this logic several times now. The trick is you don't know if you have to add an extra 1. You don't know if you have a carry coming in until the stage next to you has all of its inputs and can figure out what its carry out is. So there's a different approach, and this is called a carry look ahead adder.
I have a question about the carry look ahead
Yeah.
concept. So, would it be that instead of trying to send a number through a whole string of ripple carries,
Mm-hmm.
you make a prior decision on, well, after this one, it's just zeros, so I only need to use this many adders to solve this?
That's basically the effect of it, yeah.
Okay.
So it's a way to not have to wait until that carry has rippled all the way down.
Wouldn't you still have to do it for very large numbers?
Well, so what you're describing is a little bit different, and it's actually used in some other speed up techniques. Carry look ahead is going to actually let us figure out the carries ahead of time, even if that carry ripples all the way down to the end. It's still going to let us do our addition efficiently. But what you're describing is another speed up technique, and I can't remember what it's called. But the idea of knowing that, you know, this part of my sum is correct, right? And then just working on the earlier part of it. And there's a ton of techniques just for fast addition, and then there's a bunch of techniques for fast multiplication. And so I think all teachers hate saying this is not going to be on the exam. But I'll tell you, this is not going to be on the exam, okay? And I'm not saying that so you can, you know, leave class. But I'm saying that so that you don't need to lose the message here by worrying about, you know, my gosh, I don't understand anything this person's saying. What am I going to do about that, right? So this is like bonus material, okay? This is bonus tracks. But you'll encounter this in other courses probably, and probably when you get to a computer architecture course, you'll spend time talking about fast arithmetic. But it's just kind of a cool set of topics that use some of the things that we've been developing all quarter to do useful work. So here's the carry look ahead idea. suppose we have our adders. And we'll just go with 4 bits. So here's A0. I should do a nicer picture because we're going to use this picture a lot. Maybe. Alright, so here's A0, B0, A1, B1, and so on. And I'm not going to worry about a carry going into the original stage. We probably want to pay attention to a carry coming in, because remember, if we want to subtract, we need to add an extra 1 to do the 2's complement thing, but I'm not going to complicate it with that. Let's just think about you know, a half adder and then 3 full adders. And we've got our sum bits coming out. And let's call this carry 1. Let's look at the carries being generated. And we know that the carry coming out of this last stage, that becomes, you know, our final sum bit, usually. So here's the observation that leads us to a carry look-ahead adder. This carry coming out of here, this C4 coming out of this final stage, that's the one that's the real pain, right? That's the one that, you know, the carry potentially has to ripple all the way from here down to there. But C4 equals 1 if one of the following 2 things happen. If both of these bits are 1, we're going to get a carry coming out. Right? If you're adding a 1 and a 1, doesn't matter what that rippled carry in is. 1 plus 1, you're going to get a carry out. Your sum might be 2, it might be 3, but you're definitely going to get a carry out of here if both of these bits are a 1. So if A3 and B3 are 1, you're going to get a carry out. Or if one of those bits is a 1 and you have a carry coming in. Those are the only situations in which C4 is going to be 1. Either I have 2 1s that I'm adding together up here, or I have at least a single 1 and I have a carry coming in. So we're going to think of this a little differently. All right, so there's our 4 adders. We're going to think of a pair of outputs coming from each adder. And we're going to call these G and P for generate and propagate. So G means we generate a carry. That's going to happen when A and B are both 1. And P means we propagate a carry. Meaning if we have a carry coming in, we're going to propagate that and generate a carry coming out. Alright, so we got 2 totally brand new signals coming out of these adders, or being generated somewhere in these adders. a generate signal, which says this adder is going to produce an outgoing carry, and a propagate signal, which says, okay, this may not generate a carry based on A and B, but if a carry comes in, it's going to propagate that and generate a carry out.
So the propagate carry is just a wire from the carry in to the propagate out.
Well, no, because if A and B are both 0 and we have a carry in, we don't have a carry out. Right, this would be 0 plus a carry of 1. The sum's going to be 1. The outgoing carry is still 0. But if at least one of our inputs is a 1 and we have a carry coming in, then we'll propagate that carry. So we can write equations for these, and this actually helps clarify what these things are doing. So our generate is just an AND gate. This says if A and B are both 1, we're generating a carry. Our propagate is just a plain old OR gate. If either of these is 1, or both, then if we have an incoming carry, we'll have an outgoing carry. So these signals are trivial to produce. AND gate, OR gate. But we can use them to our advantage as follows. So let me put these in again. Alright, so let's look at carry 1. There's only 2 ways that carry 1 will be produced. One is, so let me think of this as generate 0, propagate 0. And honestly, the hardest part of this whole endeavor is pinning down your indices and not swapping them halfway through the exercise. So I'm going to call these generate and propagate 0, 1, 2, and 3, input 0, 1, 2, and 3. But the output I'm going to call, carry 1 because it's feeding into stage 1. And this will be carry 2 and so on. I could call this carry 0, 1, 2, 3 if I wanted, but it's usually done like this because this is usually carry 0 going in to that first stage. So if we use this numbering, carry 1 has the following expression. We have an output coming from carry 1 if this first stage is generating a carry. And it really can't propagate a carry if our incoming carry is 0, which I'm doing for simplicity, right? The only way we're going to get a carry coming out of here is if A and B are both 1. Right, so that's the whole half adder funniness. So if we generate a carry from stage 0, then carry 1 will be 1. Okay, it's more interesting with carry 2. Carry 2 can be true in one of 2 cases. Either this stage is generating a carry, or it's propagating a carry, and that incoming carry C1 is true. So we get a carry out of stage 1 if stage 1 generates a carry, or if it's propagating a carry and the carry going into it is asserted. And carry 3, same thing. Either we generate a carry right here, or we propagate a carry and we had a carry coming in. And C4 is generate 3 or propagate 3 and carry 3. And now we can start to blow these up because we know that carry 1 is just generate 0. So there's a closed form expression for this carry bit coming out of the second stage. It's G1 or P1 G0. And what's G1? It's A1 ANDed with B1. What's P1? It's G1 ORed with A1 ORed with B1, and G0 is A0 ANDed with B0. And we can substitute all of these in and work our way up. So carry 3 will be generate 2 or propagate 2, ANDed with C2, which is generate 1 or P1 G0, which is G2 or P2 G1 or P2 P1 G0. And we can do this one more time, and this will turn out to be G3 or propagate 3 G2 or propagate 3 propagate 2 G1 or propagate 3 propagate 2 propagate 1 G0. And each of these expressions, P and G, is just the output of an OR gate or an AND gate. And so this is an expression for this carry coming out at the end of this 4-stage adder, and it's just a sum of products, which means it has 2 levels of propagation delay. There'll be a series of AND gates that get combined together, and then we take the outputs of those and we OR them. And it's 2 propagation delays. But it's a lot of hardware, right? It's lots of gates being put together, but we're trading off hardware for time. Now, we don't usually make, a 64-bit carry look-ahead adder. But even if we wanted to add 64 bits, if we broke it into a series of 4-bit additions, 16 of these, right, the total amount of ripples we'd have to do would be 16 as opposed to 64. And so this is a win.
We use something better today still, right?
Oh yeah, yeah. Well, I mean, you still find carry look-ahead logic inside modern adders, but more stages. And this is a theme that will repeat itself throughout engineering, computer science, and probably life. There's this recurring trade-off between time and space. This is what we do with programs, right? When you have a CPU, it takes a certain amount of space, a certain amount of hardware to build the circuitry for that CPU. And within bounds, assuming you've got gigabytes of memory, right? The physical size of that hardware does not increase with bigger problems. But for a very large problem, it's going to take you a really long time to run on that chunk of hardware. Because we iterate. That's what programs do. They execute things sequentially. If you want to multiply 2 matrices, if you remember matrices from 120, it's a really simple algorithm, but it's iterative. You have to go through each row-column combination and do a dot product and add up all these products and so on and so forth. Fixed amount of hardware, but huge amount of time. If you want to add 100 numbers together in a program, right, you pull them out, one at a time from memory, you add them to a running sum. You get the next number, you add that to your sum, you get the next number, you add that to your sum. You don't need a bigger CPU, a physically larger piece of hardware, but you need more time. But if you build yourself a ripple carry adder, right, that takes more hardware, but it runs quicker. If you build yourself a carry look-ahead adder, that takes even more hardware, but it takes less time. And so a lot of problems that you can see as trade-offs between space and time, they follow this kind of direction. Now what we'd really like is, solutions down here that take very little time and space. Those are really hard to find. What we don't want are the solutions up here that take a lot of time and space. But usually there's trade-offs. And Verilog is a trade-off, right? We can build a circuit that does something, or we can take a fixed circuit and spend more time iterating. So we can build a state machine that implements a traffic light controller. We could also make a giant lookup table that implements a traffic light controller. Right? All you need to know is what are the states of each of your 9 lights, what are the states of your 3 car sensors. That's 12 inputs. There's 4,096 combinations of 12 inputs, and for each one we can say what should the lights do. And it's just a gargantuan truth table. But it's really fast. So if we think about multiplication, you know, when you want to multiply binary numbers, it's the same thing we do when we multiply decimal. We just take this digit and we multiply that by the number. And 0 times 1001 is 0. And then we take this digit and multiply by the number. And we take the third digit and multiply by the first number. And we take the fourth digit. And then we add them together. Well, this is easier than working in decimal. When we multiply this number by each digit of that number, we either multiply by 0 or 1. If we multiply by 0, the product is just 0. If we multiply by 1, the product is just that first number. So we don't really need to do any multiplication at all. We just need to write down either a 0 or that first number and keep shifting it over. Well, this is just an AND operation. If we take each bit here and we AND it with a 0, we get zeros. If we take each bit here and we AND it with a 1, we get back that original number. So multiplication is really just using an AND gate. And shifting these things over, well, we know how to make shift registers. We can do that with D flip-flops. And just, you know, take the output of one, feed it to the input of a next. Tick a clock. Each time we do that, this will shift over. And we arguably know how to do addition. Well, if we do this, you know, 2 numbers at a time, we take this and add it, we get a running sum. We take our next number and we add that, right? And this is mimicking pencil and paper multiplication. And so you can build a little state machine that basically takes one number, starts working through each bit of a second number, and wherever it finds a 1, adds that first number to a running sum, but also as it moves through, keeps shifting this first number over, so it looks like that, and so on. And if you have a big enough adder, you just keep adding these to your sum, and when you're done, you've got your product. The downside to a state machine like that, though, is time. If I'm trying to multiply 16-bit numbers, I have to loop 16 times to deal with each of the 16 bits in here. But there's other tricks we can use for multiplying numbers. I could build a large combinational circuit that would do the same thing as this, but without having to loop. And basically, all I need to do is have a bunch of adders situated like this. And, you know, take the output from one and feed that into an input of the next one. And so that's one of the bits I'm going to add. And the other bit I'm going to add is, let's say this number here is called A. Right? So this is going to be This is going to be ANDed with, let's say this is B. I'm going to take this number and I'm going to AND each bit of it with this least significant bit of B, which will give me either, you know, the bits of A or a 0. And that's the first thing I'm going to put into my adder. And I'm going to take the sum from that, and I'm going to add to that my number A ANDed with the second bit of B. So my second bit is a 1, so this is going to be a 1001, and that's going to get added to whatever was produced from that first sum. And this is a purely combinational circuit. Now it's got a lot of propagation delay because, you know, my sums have to come out of here and go into the next stage and so on. And if you've got ripple carries, these sums aren't correct until, you know, the carry generated from here moves all the way down here, but you can use carry look-ahead logic and so on and so forth. But I can implement this without any looping at all. What do you think the fastest way is to the fastest circuit you could build to multiply two 16-bit numbers? How could you really pare the propagation delay down to be as small as possible? Any ideas?
The best idea I could have is having like a register store the number you put in and the number of times you want to multiply it, and you would add it that many times, but then you'd have to loop over the same thing again and again.
Okay. That's good though. That would get you the answer. Can we do better?
I think we can.
I probably wouldn't be asking if we couldn't. Two 16-bit numbers, A and B, 32-bit product, P0 through P32. Can I fill in this truth table? Could you fill in this truth table?
That would take way too much time.
It would take a lot of time.
Yeah.
Too long for an exam question. But this is a system diagram for a 16-bit multiplier. Two 16-bit inputs A and B, 32-bit output P, where P is equal to A times B. You can write a truth table for that. It is a big truth table. So we have 32 inputs. That's 2 to the 32nd rows. That's 4 billion rows. And 32 outputs. So that's 128 billion ones and zeros over here. It's a big truth table, but you could build a single sum of products for each of these 32 outputs, and there's your circuit. There's a multiplier. And it takes 2 propagation delays to give you your product. Basically the time to calculate your AND terms and then to sum those together. So this is really efficient on time, but wow, it's a dog on space. But you can do that, and in fact most of what we do with circuitry or with computer programs can be reduced to a lookup table, which is what a truth table is. So when I was a kid, I had this what I thought was a really cool book. It was a book of tables, and you would, I don't think I have this on my shelf here. I think it's still on my shelf at school. But it was a book of sines and cosines and logarithms and squares and square roots. And if you wanted to know, what the logarithm of 23.7 was, you'd flip through page after page after page till you got to the 23s, and you'd go down to 23.7, and there'd be the logarithm written right next to it. And if you wanted to know the cosine of 15 degrees, you'd go to the cosine chapter, and you'd go through the table 13, 14, 15, and there would be the cosine written next to it. Right? This is what people used before we had computers and calculators. People were doing scientific calculation, long before that, and they had lookup tables, books that had all these results of calculations in them. Well, we can do the same thing with digital logic. We can build digital versions of those books, those lookup tables, and do really fast calculations, but at a huge price, which is needing a lot of hardware. This goes back to when we talked about programmable logic. We had PALs, PLAs, and PROMs. And a PROM had a programmable OR plane, right? And we talked about it as a form of programmable logic, a way to implement, say a sum of products expression to perform some kind of operation to change inputs into outputs. But a PROM is really a programmable read-only memory. It's really just a lookup table. And the most common use for PROMs is to store, immutable code for, say, the boot up or the BIOS of a computer. You would have a chip that would actually store the ones and zeros of the instructions that get your machine running. That's stored in a PROM. So is it a lookup table of ones and zeros, or is it a piece of programmable logic? It's both. They're the same thing. And that gets into a whole philosophical discussion that I won't take you into. But it's something to think about. Alright, let me show you one more trick. This is related to fast multiplication. So let's think about multiplying numbers in binary. Let me grab my pencil. All right, suppose you're asked to do the following multiplication. Could everybody do that? If you saw this on a final exam and it was like multiply these two numbers in binary, would that cause more than a moment's panic? Probably. Well, it might cause panic, but if it was on a homework question, right? So forget about the exam. If this is a homework question, right? Would you be like, oh, I'm gonna have to cancel my weekend plans because I got to multiply these numbers? No, you look at it and you think about it, and it's really easy to do this, right? The answer is just going to be that. I'm just multiplying it by 1. Not a big deal. Everybody see that?
Yeah.
Right? So, I mean, if you did it longhand, you'd multiply this by 1, and you'd write that number down, and then all these other bits, you're going to multiply this by 0, you're going to add a bunch of zeros, right? And you're just going to end up with that number. Alright, so then you go on to question 2, and it says, do this multiplication. Well, we're not just multiplying by 1 anymore. but we're doing something almost as painless. This 0 times all of this stuff, you know, when we do decimal, if we have a 0, we just carry the 0 down. And then when we multiply this by 1, we're just going to do 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0. And all these other zeros are going to be ignored. There's our answer. Right? It's really not that much more work. And that makes sense if you think about the fact that this is the number 2. When you multiply a number by 2, really all you have to do is shift it left one spot. And that's what our answer is. It's just this original number shifted left one position. And if you go on to the next question, and it says do this multiplication, well, now you know you've got a pretty good handle on what's going on here. You know, oh, this is just another little trick, right? So all of these zeros will just come down directly, and then this 1 says multiply this by 1, and I'm just going to copy this number down directly. There's my product. And these other zeros aren't going to affect anything because 0 times that first number is 0. So if you're multiplying a binary number by something that has a single 1 in it, it's really, really fast. All you got to do is basically just shift your original number over a certain amount. And this is exactly that. Alright, so let me show you the question you don't want to encounter. Suppose you're multiplying by that number. Does everybody see that that's going to be a lot more work than the previous cases?
Yes.
Right? Because every time we have a 1, we're going to have to copy that number down. And we're going to have to keep things lined up in columns, which I'm not good at doing, and so on. Then we're going to have to add them all together. Blah. That's a nightmare, right? So if we had a single 1, life is good. If we have a bunch of 1s side by side, life is not so good. So here's what Booth's algorithm does. It makes the observation that this is really this nice number minus 1. Anytime you have a bunch of 1s, that's the same thing as this number, a 1 with a bunch of zeros, after you subtract 1 from it.
That's a nice way to think about it.
Yeah, it's a really nice way to think about it. So if this number up here is A, and I want to calculate A times that, that's the same thing as A times that minus A times 1. Well, let me not skip a step. Right, since that number is the same as that, this product is the same as A times this number minus A times 1. Well, this is really easy to calculate. That's what we did those first 2 or 3 examples. That's just A shifted over. And this is really easy to calculate. A times 1 is just A. And so instead of multiplying all of these 1s and getting all these numbers and shifting them and adding them together, we could calculate this product by simply taking A, shifting it over 9 spots in this case, and then subtracting A from it. And that works any time that you have a series of ones. So if you have some number A, and you want to multiply by this, what you do is you basically take this part of your multiplication and you say, instead of multiplying A by 3, I'll do A times 4, and I'll subtract A. And then when you want to do this part of your multiplication, you rewrite it as that. And so Booth's algorithm basically replaces each successive pattern of ones with a pair of operations. Shift your number over a certain amount and then subtract one copy of your number. And so you can build hardware that does this and does very efficient multiplication by reducing the number of add and shifts that you have to do. And the speed up, depends on how lucky you are with this number. If this number is something like, this, you're not going to get that speed up. But anytime you have repeated ones, you can take advantage of that and get a much faster multiplication. So that's Booth's algorithm, and it's one of a number of very clever approaches to doing arithmetic. The other thing I'll just mention, and I'm not going to go into details, but along the lines of multiplication, something called a Wallace tree, and we still use Wallace trees in multiplication hardware today. And the idea of a Wallace tree is you're multiplying numbers together, and you need to do all of these additions. So picture, doing your add and shift, and you end up with a bunch of things that you need to add together. Well, I can calculate each of these partial products in parallel, right? This is my first number times bit 0, my first number times bit 1, bit 2, bit 3, and so on. So you can calculate those partial products in parallel. And I can add these bits together very efficiently. But we've got the carries to deal with. So a Wallace tree is a way to basically say, let's just add our bits, and let's generate a sum and a carry from each of these, and let's make some adjustment to our final sum at the end. And so imagine you have 64 rows of numbers that you're trying to add together. Well, we can just add each column independent of what's going on in the other columns, and generate the sum and carry for each of these 64 columns of numbers. And then by going back and looking at the sums and carries, after you've done all of this addition, we can make the corrections we need to actually get the correct final sum. And so instead of constantly rippling the carry on each of these stages of addition, just add sort of blindly, ignoring the ripple effect, and then make a correction at the end. That's the basic idea of a Wallace tree, and you get tremendous speed up. It's like a log n kind of reduction of work, and it's super clever. And there's you can spend a week or two just studying Wallace trees in a computer architecture class.
That's like the algorithms course. I forget what it's called. There's like a CSE course for that, right?
At a university there would be, yeah, not at Clark, but like at WSU there'll be a computer architecture course, and it depends what area you're doing, what electives you take, but you'll probably encounter this in a future course at a university. All right, so that's a really kind of high level view of just looking at some of the things that can happen. All of this is built, you know, using things that you already understand, things you've already worked with in this course and used in other applications. It's really just different applications of the same concepts. And stuff you'll probably see down the road, and it's fun stuff when you get to it. All right, so Thursday, my only plan I think is to talk about the final exam and kind of, you know, rehash everything we've talked about. That will be a really boring class unless you bring questions and ask questions that you care about the answers of. So my suggestion would be, you know, go through what we've done, look at homeworks, labs, and maybe the midterm, and see what you have questions about, what you're not quite totally clear on, and so on, and ask about those on Thursday. We can talk about whatever you want, and that'll be more fun than just hearing me kind of drone through 10 weeks of material in 2 hours. So, all right, cool. That's all I got for today. Come by office or lab hours if you got other questions. Otherwise, I will see you on Thursday. Thanks.
Thank you.